Kia ora koutou. This video is for my 13 MCA class this year, and it's to go over the dot product and to prove the result that we got near the end of last term about the angle between two vectors. So I'm doing this because I feel like we rushed it quite a lot in class, and also because there were a few people away. It's going to give you some good practice at the dot product. I'm going to prove a couple of really simple little results, and then we're going to see why we get this really important result here, which is that the cosine of the angle between two vectors is given by, sorry, trying to get my stylus working, is given by this. And this turns out to come straight from the cosine rule. Okay, so let's go back to thinking about what the dot product is. If I've got two vectors, suppose I've got u, and I'll do it in column form, so u is u1, u2, u3. So it's a three-dimensional vector, and v is v1, v2, v3. Then we learnt last term that the dot product is defined as this. So we simply take this and times it by this. So we get u1 v1 plus u2 v2 plus u3 v3. So the dot product is a scalar, right? It's just a number, it's not a vector. Then the next thing that we went on to just state after we'd done some practice with that is that we had this result that the angle between two vectors is given by the dot product of the two vectors divided by their magnitudes. And I talked a little bit about intuitively what this was doing was scaling my dot product so that I ended up with a number between -1 and 1, right? So one of the important things that we learned already is that if we've got two vectors and they're perpendicular, then the cosine of 90 degrees is 0. So if we're looking for perpendicular vectors, the way to find them is to solve this thing here. But none of that really told me where this nice result came from. So we're going to do that now. So I just want to note before we get started that if we look at the magnitude of a vector, we get this. Right, so the magnitude of a vector is basically Pythagoras in 3 dimensions. And if we square the magnitude of that vector, we lose the square root sign. I don't know why the stylus is doing the weird flicky thing. Sorry, guys, but it is. So we've got that result. And then if we look at what that's the same as, that is the same as v dot v. So the dot product of the vector with itself. So we'll just work through that slowly so that you can see it. We're going to use this result when we prove the result about the angle. So v dot v is equal to v1 squared plus v2 squared plus v3 squared, right? Because the dot product is where I just do this. This times this, plus this times this, plus this times this. Right, so we've got this result here. So that's quite good. Now the next thing I'm going to do is to draw a little picture of what we mean by the angle between two vectors. So suppose this is vector v and this is vector u. This is the angle in between them. Now we know from our basic vector work and vector geometry that if I wanted to turn that into a triangle, then this vector here would be vector v take away vector u, right? So now we've got a non-right angled triangle. And if we just go back and look at the cosine rule, we can remember what that tells me. Nothing to do with vectors, but if I've got a theta here and I label these sides A and B and C, then we have cos of theta is equal to A squared plus B squared minus C squared over 2AB. Right, so what I'm going to do now is I'm going to take this result and I'm going to transfer it up here to my vector situation. So I'm going to erase this now, and we can get going. So we can say that cosine of theta is equal to the length of this side squared plus the length of this side squared minus, what have I got now? Minus the length of the third side squared divided by 2 times make that look like a V, minus that, right? So that's going to get me directly to my result. Now remember that we just proved something useful about this and indirectly about this, and we'll do a little bit of work on the magnitude of that third side. So straight away we can say that cosine of theta is equal to v dot v plus u dot u, right? Minus this, divided by 2 times the magnitude of v times the magnitude of u. So let's have a look at what this is. Well, the magnitude of this squared is equal to the magnitude of v1 minus u1, v2 minus u2, and v3 minus u3. And we know how to find that. That's equal to the square root of this thing here. So magnitudes with vectors are really easy to find, and that's what I'm doing in this step. And that means that, oh, I'm finding that squared, so it's the magnitude squared, which is nice because it gets rid of the square root sign. And now I can expand all of this out, because remember what I'm going to use it for is I'm going to substitute in here, and I'm going to hope that some of this stuff disappears when we combine everything. So here I'm going to do my expansion like this. I'm going to get v1 squared plus u1 squared. I'm going to come back to that cross term at the end, right, and plus v2 squared plus u2 squared plus v3 squared plus u3 squared. Now I have to take out all of the crossover terms, so minus 2v1 u1, minus 2v2 u2, minus 2v3 u3. Right, so let's see how we can combine some of that. Well, remember up here we've got v dot v. V dot v is the same as this, and u dot u is the same as this. So this equals v dot v plus u dot u minus 2 times v1 u1 plus v2 u2 plus v3 u3. So that's this. Now we can simplify this to be v dot v plus u dot u minus 2 v dot u. Just let me get rid of, there's no dot there, there's just a u. Okay, so what we've done by doing that step out to the side is that we've shown that we can rewrite this like this. So going back to here, we're going to substitute in. So star gives me this. Cos of theta is equal to v dot v plus u dot u minus v dot v plus u dot u minus 2v dot u divided by 2 times v, the magnitude of v, times the magnitude of u. And you should be starting to feel really happy now, because we can see that what we've got here is v dot v take away v dot v, u dot u take away u dot u, and we're left with 2 times v dot u over 2 times the magnitude of the two things. And that gives me my final really nice result, which is this one here. So there you go. Hopefully for those of you, lots of you who like understanding where our results came from, that will make you feel a little bit better about using that one. This is a result that you will use over and over again. It's incredibly useful to both be able to go from two lines to find the angle, and sometimes to go from a condition where we know that the angle is something and working backwards. And that's especially the case where you're looking for perpendicular vectors. Okay. Thanks for watching, and just email me if you've got any questions about that or any specific old problems that you've been working on with vectors.